When engineers need to measure motion and position, magnetic sensing is a go-to touchless technology that's embedded into devices we all use every day. But there's no one-size-fits-all solution. There are design considerations, trade-offs, and rules of thumb you have to follow to get the most out of your design. So in this tech chat, brought to you by Mouser Electronics, I'm joined by a magnetic sensing pro, Nick Czarnecki, product line manager at Allegro Microsystems, to talk about 3D magnetic position sensing. We'll unpack Hall effect sensors and the types of motion they can measure, as well as how to think through magnet selection, sensor placement, calibration, and packaging. Nick, thanks for being here today. I'm looking forward to this.
Thank you for having me.
I'm curious, what sorts of people are interested in 3D sensing, and can you kind of give me an overview of what the technology is and looks like?
Sure. So people that are interested in this type of technology are really people that want to measure motion. So typically these could be used for measuring rotary motion, anywhere from 0 degrees up to 360 degrees of rotation, linear motion or translation, so forward and backward or left and right. All the way up to things like joystick sensing, like you might find in a game controller or like industrial joystick. At its core, the technology is based off of magnetic principles. So we pair our sensor or our integrated circuit with a magnet. And by utilizing Hall effect technology, we're able to measure the 3 magnetic field vectors, so an X, Y, and Z axes. And by doing some measurement computations on those, we're able to determine, the rotation or translation or joystick motion of a magnet in vicinity of the IC.
So talk me through a little bit about like crash course on what is the Hall effect, and then how do you actually practically implement that in silicon?
So the Hall effect is used to measure magnetic fields. What it is you can imagine it's basically a very thin sheet of material. We apply a current through that material. And if there's no magnetic field present, the current basically spreads out evenly through that sheet of material, which means there's no voltage differential when you measure on the side of it. However, if you apply a magnetic field, the current will actually deviate. It will move because of the Lorentz force, and that creates an unequal charge, and then we can measure that. That's a voltage. And it applies both for positive magnetic fields and negative magnetic fields. It will just move the current to the left or to the right, if you imagine it that way. And that means you can measure both the magnitude as well as the direction of the field. So if it's going forward into or out of the plate. And then we simply cascade that out. So we use planar Hall effects for measuring the Z magnetic field. And then we use vertical Hall effects to measure the X and Y magnetic field.
So essentially you have 3 one-dimensional sensors into one package, or is it on the same die?
Exactly. It's all in the same die. So it's a monolithic process. And that little insert image you see there, the Z in blue, the X and Y in orange and green, that's basically how we lay it out on the integrated circuit. We have one planar Hall plate, and we put 2 vertical Hall plates right next to it. So it allows us to sense in a very tiny area the 3D magnetic field.
And who is putting these into their designs? You mentioned people who care about motion and position, but can you give me some maybe more concrete examples of places you see these get used?
Yeah, it's very common in automotive applications. So things like throttle bodies or exhaust gas recirculation valves, coolant valves, etc. Really where the non-contact in nature comes into play because it enables long life sensing. They're very robust against, say, contamination, dust, dirt, liquids. But we also see that throughout other industries as well. So I mentioned industrial joysticks in the past. That's a common application. General purpose sensing, just detect up and down motions, door open close detections. We also see this on two-wheelers for things like throttle control again, for the twist throttle on the scooters. And then consumer electronics. We can see this in things like security systems or game controllers potentially as well.
Okay, I never thought about the drive-by-wire. I always figured when I twisted the handle, there was, back in the day, there was a cable, but it makes 100% sense that you do that magnetically. What is the craziest product or project you've seen, or one that stands out to you with magnetic sensing?
Oh, that's a good question. I would actually need to think on that one a while. One of the ones that I like, especially recently, are where they're using our sensors in these industrial transport applications. And I have a picture of that later on. But they use arrays of these sensors to detect multimeter motion. And they measure these platforms as they move along this magnetically levitated track. And they're used to basically move components from one part of the assembly line to another to do different operations for things like assembling phones or other consumer electronics sort of products. You can use them in pharmaceutical industries as well. It's a really cool application.
What sort of range can you get out of these chips, or does it depend on like the magnet itself that you're using?
It depends on the magnet. So for rotary motion, you can do 0 to 360 degrees with a single magnet. If you go beyond that, the output signal just repeats. So it's a sawtooth at that point. For linear motion, there's a rough rule of thumb that the magnet should be about 1/2 of the stroke length. So if you're doing a 20 millimeter stroke, for example, you should use about a 10 millimeter long magnet. In that case, it'd be a rod magnet. Okay. Now, if you need to go further, you can do things like arrange 2 magnets that could get you a little bit more range, maybe up to, say, 50 millimeters. But generally speaking, with one magnet, you're about about 30 millimeters. That's plus minus 15 from the center of the sensor. And that's why for this long linear application, they use multiple sensors in an array on either an I2C bus or a SPI bus.
Okay. I was going to ask about the chip output, because the input into the chip is magnetic flux, I suppose. And then the Hall effect is getting sensed. You're doing a voltage, difference measurement. And then is it communicating out through a serial protocol like that, or just an analog value? What's kind of the typical output for these?
Yeah, it depends on the product that you're using. We can output analog signals. Typically, we'll do up to 2 channels. So let's say an X signal and a Y signal. That could be like a sine cosine sensor, or an X and Z. In most cases, though, customers will want something a little bit more integrated. So going back to like the automotive industry, they'll use something called SENT, single edge nibble transmission, or they'll use analog output, or they'll use PWM. Those are most common protocols, I would say. Okay. For other applications, consumer or embedded applications, SPI and I2C are very common, and we support those as well.
So kind of your anything you could want for your system, you can get out of these.
We pretty much run the gamut for the output protocol today, yeah.
So how accurate are magnetic sensors? Are they like what sort of resolution do you get?
Yeah, so typically resolution is in the range of 12 bits. In terms of accuracy, you see that's in the middle point there. We generally specify 1 degree before calibration. So that means the accuracy that you'd get from our sensor before you do any sort of end-of-line calibration. That's assuming that you're applying an ideal magnetic field. The note below that says after calibration, and that's an end-of-line calibration that's done in the customer application after you've integrated the sensor plus the magnet into the application. And the reason why that's typically done is 2 reasons. One, you can tune the output span to the desired value. So if you're measuring a 0 to 90 degree range, or a 0 to 180 degree range, or 0 to 360, or anywhere in between, you want to be able to say it's going from 0 to 100% output, or thereabouts. The other reason is to improve the accuracy. So we have multi-point calibration in our sensors, which allows you to reduce the error at each of those points. So you may be able to move the magnet to 0 degrees and you program a desired output value, and you move it to, say, 10 degrees, program it there, and so on and so forth. And each time you calibrate it at those points, you're reducing the residual error. And that residual error is not only coming from our sensor, but it's coming from the actual application itself. The tolerance of the magnet placement. If you have eccentricity or tilt or anything like that, this end-of-line calibration step really helps to reduce that error and improve the accuracy.
So if you really care a lot about accuracy, it's important to have kind of a calibration and test plan to make sure that once it's actually implemented in a final production design, you're able to do that kind of sanity check and refinement of the calibration at the end of the line.
Exactly. And that will depend on your application. So some customers will be able to start from a very accurate initial point. This is typically a rotary on-axis application. Those are the easiest and the most accurate to start with. Other ones like linear motion, if you're using a very tiny magnet, or maybe you just have a very poorly tolerant system, there you may want to have that calibration step in order to get that accuracy that you need.
You mentioned magnet size and position and a couple of these different movement modalities. Can you talk me through each of these 4 different motion profiles? Maybe why you would use one and what makes them, or maybe some tips for how to implement them if you're looking for that specific profile.
So really, we don't specify which configuration you want to use. That's coming from the application needs itself. So if you're measuring like a valve that needs to open or close, like a butterfly valve, that's almost certainly going to be rotary motion. Now, if you want to use rotary on-axis motion or rotary off-axis motion, that'll depend on the system and whether or not you can put a magnet on the end of the shaft. So rotary on-axis motion, the one on the left, is where you have a magnet positioned above the sensor, and the rotation of the magnet is coincident with the sensing spot of the sensor itself. That's represented by that vertical line. That's probably the most common configuration, I would say. It's very easy to implement, almost like a plug-and-play application, I like to call it. You just buy a magnet, you buy the sensor, you put them on top, and you're pretty much good to go there. You get very good performance that way as well. Rotary off-axis, though, is very common as well because in some cases, if you have a cover or a bearing at the end of the shaft, you maybe can't put the magnet there, right? So you might have to put the magnet off to the axis. And while we show it here as a solid disc magnet, in a lot of cases, customers will use a ring magnet and they'll basically slide it over the shaft. And that also works. And that's a way that you can do a different sort of packaging. Linear motion is just like you see there, the magnet's sliding by back and forth. That's usually using a rod magnet. Again, size is about 1/2 of the stroke length. That gets you your best nonlinearity, your best accuracy. You can go smaller, you can go bigger. It all depends on the constraints of the system. That gets you about 0 to 30 millimeters. And then joystick motion, shown here, going kind of back, left and right. You can also do forward and backwards. So you can do forward, backward, left and right motion to do, a typical joystick application.
I had to wrap my head around a little bit how the joystick motion would actually be usable, how you would tell, maybe 45 degrees left from 45 degrees right. But then once you add the other dimensions to it, I was just thinking, and maybe X dimension.
It kind of goes into how we actually use these sensors, because measuring the raw vectors, right, the X, Y, and Z vectors is neat, it's interesting, but you need to be able to do something with it, right? You want a signal that's proportional to your motion, because that's where you eventually charge a sense. So for all these devices, or not all the devices, but most of the devices, customers will want an angle output. They want a value output that's proportional to the motion. And that's proportional to either the rotary motion, the linear motion, or the joystick motion. And the way that we do that is we measure 2 or 3 vectors, X and Y, X and Z, Y and Z, or X, Y, and Z, and we put those into an arctangent calculation, an angle calculation. And there's a couple of reasons why we do that. One is because for the rotary on-axis motion, which is probably the easiest to conceptualize here, as you rotate that magnet, there's a vector that's basically pointing planar, parallel to the face of the package, and it's just spinning around in a circle. So it's spinning, it's pointing up left, and then up right, and then down right as you rotate the magnet around. And if you measure the X and the Y components of that vector, it's a sine and a cosine, right? You're getting a sine and a cosine signal. Well, if you put that into an arctangent, the cool thing about trigonometry is that you put sine cosine into arctangent, you get a nice angle output that's proportional to the rotation then. So that means that we can then process that angle to give you a analog signal that's proportional to the rotation, be it from 0 to 5 volts, or it can give you a SPI representation of that angle, or an I2C representation. And that kind of processing, that angle calculation, scales throughout all these motion types. So you can do that for linear motion. While you don't get a perfect sine cosine signal with that linear motion, you get close enough that it works. And joystick is the same way. You push it forward, backward, and you're getting the kind of sine cosine on X and Z. You move it left to right, and you get a kind of sine cosine on Y and Z. And you get a magnetic angle that way. once you do that calculation.
That it makes sense. Like it's easy to get buried in the physics of what's happening, but at the end of the day, you're trying to read out a value and then make a decision based on that value and feed that into your actuator or whatever you're trying to do. So getting actual insights is more than just here's the magnetic strength at this position. It's here's the actual data you want.
Exactly.
So once you kind of have an idea of the movement modality you want and you know what kind of rough arrangement you'd like to have, what are some practical recommendations or suggestions for people who are trying to actually go in and mount their magnet, mount their sensor, and make sure it's set up in a way that's going to work for them?
One of the things that you need to be concerned about is selecting the right magnet, right? So you can buy magnets from all sorts of different places. I like to buy them online because they're usually off the shelf, inexpensive. One thing you need to watch out for is make sure you buy the right magnetization of magnet. You can buy axially magnetized magnets, which are magnetized through the face, or you can buy them as diametric magnetized magnets, which are what's shown here, where they're magnetized through the edges. If you buy an axially magnetized magnet for rotation motion, you're going to be disappointed because it's not going to work, because that vector is not changing then. So that's one thing to watch out for. The other thing to watch out for is that you need to make sure that the magnet you buy is of sufficient strength. So you want to make sure that the magnetic field that's generating is within the datasheet specifications, say 200 Gauss or 20 milliteslas up to around 1,000 Gauss or 100 milliteslas. If you exceed that, on the high end, our sensor won't be damaged. It'll still work just fine once you remove the excessive field. On the low end, if you go below that, you'll still suffer a penalty in things like noise or inaccuracy. But again, there's not going to be any damage. So just to make sure that you're performing within the datasheet specifications, you want to make sure that the magnet is strong enough that's operating within that ideal range.
I never thought about magnet shopping discussion, but it makes a lot of sense that it would be very disappointing to buy the wrong magnet.
It's happened before in my past where customers have bought a magnet and they put on there and they're like, it's not giving me an output.
Your sensor's broken. Yeah.
Yeah. So then you need to make sure that you're using the right magnetization of the magnet. You want to make sure that you're getting that sine cosine field change as you move the magnet about.
You mentioned removing excess magnetic force, magnetic field when the magnet was too strong. Is that like, how would you go about even doing that?
Yeah, it's really going to be changing the magnet. So using the weaker magnet, potentially smaller magnet. You can also move the magnet further away because the magnetic field decreases the further away you get from the sensor, right? So that's one way you can do it as well.
So you're not like hitting it with a blowtorch or something.
So funny you should mention that. I mean, theoretically you could, but I imagine you hit that Curie point and the magnet demagnetizes. So there's probably a very fine line you'd have to ride on that one. It's probably easier just to buy a weaker magnet.
That makes sense. What are some other magnet shopping tips? Like you can go on the internet and just get magnets, but how much does supplier sourcing matter? Do you have even like recommended vendors or is it kind of a normal procurement challenge?
It's really a normal procurement challenge, I would say. There's really 4 different types of magnets out there, 4 different chemistries. There's ferrite, alnico, and then the rare earth types, the samarium cobalts and the neodymiums magnets. All of those can work, again, as long as you're within the right magnetization, the right vector direction, and the right field strength. We see a lot of people more interested in ferrite magnets today for supply chain resiliency. They're also lower cost, so that's one thing to pay attention to. They're generally bigger magnets, though. They're lower performance. They have lower field strength, so there is that trade-off. You might have to have a bigger magnet than you otherwise would. But overall, they're pretty standard sourcing, I would say.
I guess it depends a lot on your application, which magnet you would end up, like if you can afford in your design budget to have the weight of a ferrite and make it work, then that maybe opens up some options for you depending on how the world changes over the next little while. Let's talk a little bit about packaging. So is this all kind of standard packaging, or are certain types of packaging better for different applications?
Yeah, so we support 2 different main package types, which you see on the screen here. The one on the left is very standard PCB mounting. So we support things like SOIC8s or TSOP14 packages. Those are, typically single die for us or dual die. So we also have redundant dual die package options. And we support leadless package as well, like DFN10s, which offer smaller size than the SRC8s and TSOP14s. It really depends on what customers want in the end, and if they want to do things like automatic optical inspection, or if they could do X-ray inspection, or maybe even no inspection at all, and how many dies they want in the application for redundancy. So these are all standard surface mount options that you run through a standard reflow process.
What sort of redundancy would people be looking for? Is it in case one measurement fails, or is it a noise resiliency thing?
It's for safety primarily. So in the event that one die does have a failure, then they can rely on the other die for, say, a walk-home condition, for example. You can still fail safe, but you can still maybe fail in a kind of reduced operational range. Some customers want dual dies because they like the resiliency of having dual dies, but it's generally related to like a safety and redundancy and potentially availability case. The dual die I'm talking about as well, just for clarity, is a homogeneous dual die. So we take two of the same dies and we stack them on top of each other. So we have two of the same magnetic sensors inside.
Interesting. As much as I want to dig into that packaging challenge, that's maybe another discussion. What is the kind of edge conditions of where these work, since we're on the topic of them failing? Is it like, is there a temperature or a physical, motion component to this? When do they kind of run into practical limits of where they're useful or where they're not?
Yeah, so I would say the harshest industry we operate in today is the automotive industry. And that's where we support ambient operating temperatures from -40 degrees Celsius up to 150 degrees Celsius. So that's about the limit. You can go a little bit beyond that, short excursions, and the sensor's not going to be damaged in most cases. But that also means that they're very robust against, contamination because they're non-contacting again. It's because they can, support vibration. So that's really the edge that we operate in.
So I know that there are PCB-mounted magnetic sensors kind of everywhere, but I have to imagine PCB-less is also very popular is it for larger designs, or what are people thinking through when they don't want to put the sensor on a PCB itself?
Yeah, it's actually for small designs in a lot of cases. We see this a lot in harsh media applications, industrial and automotive especially. And the reason why PCB-less is so popular is because of a lot of reasons, actually, but one is it's more robust to the environment. You don't have to worry about vibration, potentially. You weld the terminal leads directly to a connector lead frame. You can encapsulate or pot the sensor itself, so then it's immune to, oil or fluids. You get very good EMC performance because we integrate the capacitors that are needed for like transient suppression inside the package. And then the other reason is that you can make it very, very small. So you don't have to have a PCB there. So it's a thinner package typically. And then finally, the other reason is you simplify your supply chain. You don't have to have a contract manufacturer build a PCB for you. You don't have to buy any other external components. You simply buy this one sensor, you put in an application, you weld the leads to the connector lead frame, and you're basically done. You have a nice sensing solution that way.
That makes a lot of sense, that you can essentially, the sensor is maybe more robust than a PCB assembly. So being able to use just the sensor and then pot it, like you mentioned, would give it a lot more, resilience. So as we start to get into new applications, can you talk me through, you mentioned industrial automation sort of manufacturing line. You want to maybe dig into that a little more and what that might look like?
Yeah, so that picture is kind of an AI generated image of the example I was talking about earlier, where they can use multiple sensors in an array in order to measure these platforms as they slide along these industrial conveyor belts or these industrial linear platforms. That's typically one sensor per platform, and then the sensors basically hand off via an external microcontroller the presence of the magnet as they slide by. But we also see them all over the place in, again, things like joysticks or other measurement devices.
Yeah, I remember as a kid taking apart one of my Nintendo 64 controller joysticks because it just kept acting up and realizing I was way over my head. So maybe that's part of my electrical engineering origin story. I don't know. Coming full circle here. You also mentioned throttle bodies earlier. Can you talk me through, and you have background in the automotive industry, what does it look like to use magnetic sensing, especially in maybe the electric vehicle market where I have to imagine the environment is kind of magnetically noisy?
It can be, yeah. So that's something you need to watch out for with any magnetic sensor. So as things move more towards electrification, there are things like straight magnetic fields to watch out for. So the sensors shown here are not insensitive to straight magnetic fields, but there is a rough rule of thumb that guides you on how much disturbance there may be. And that's basically 1% of the good field produced by the magnet injected as a kind of stray field or bias field gives you 0.3 degrees of angular error. That scales linearly, so if you know how much stray field you're going to apply to the sensor, that's how much deviation you're going to get. Generally speaking, since magnetic fields decrease very quickly over distance, unless you're like right up against a current carrying conductor or another very big magnet, you're not necessarily going to see a huge amount of deviation due to fields in the electric vehicle.
So you probably don't want to put your throttle body right next to your drive motor, for example. But
no, generally not. But I have heard stories about some OEMs where they routed current carrying conductors next to things like a throttle body. And when you really hit not the gas anymore, right? But when you hit the accelerator pedal, you actually see some disturbance coming on because of that. So it's a packaging thing that you need to watch out for sometimes as well. So really what this slide showcases is that it's very easy to integrate these devices. So it's really sensor plus magnet and you're effectively done. Obviously, I'm simplifying it a little bit. There are things like programming it for the desired output span. These devices are typically calibratable at end of line to minimize the amount of angular measurement. To say for a throttle body, you're measuring 0 to 90, you want 0 to 100% output span, right? You don't want to be able to measure 360 degrees because that valve doesn't spin 360. So again, these devices are programmable, which makes them very flexible. You can fit the sensor to the application rather than fitting the application to the sensor. And these really excel at these sorts of standalone operations like throttle bodies or valves or general purpose actuators.
Talk me through the kind of calibration process or at least thought process. Like you said, if I know it's only going to be 0 to 90 degrees, is it a matter of selecting the right sensor that does a 0 to 90? Or is there some way I can burn a register or something like that?
You can burn a register. So it's EEPROM, so it's not one-time programmable. So for example, if we take the 31315 device shown there, that's one of our angular sensors that can output analog, PWM, or scent output. You pair that with a magnet. You put the magnet at the end of the shaft for the valve. And then once you do that, you put the throttle body into an end-of-line test stand. And then you can communicate with our sensor through the output pin. So all you need to do is plug in power ground output, and then we communicate through the output pin to program the EEPROM. And what typically happens is customers will move the valve to the first position, and they'll say, we want this to be 0% output. And then they'll move it to the open position and say, we want this to be 100% output. And you can program our sensor to say, all right, we can configure a transfer function, that has a certain slope. And that allows you to say, we want this rotation range with this output span for this application. And that means that you can use the same sensor across multiple applications. So if you have a throttle body that's 0 to 90, you can use it for that. If you have a kind of linear stroke for a poppet valve, you can use it for that as well. Because again, it's just tuning the angle or tuning the output to a given angle measurement range.
Fascinating. So you could use the same sensor for multiple applications, and then you save yourself all sorts of headaches by having, simplifying your supply chain and making your R&D implementations kind of potentially somewhat uniform across the whole system.
Yeah, you'd have one sensor to manage. You don't have to do multiple qualifications. Once you've proven out, it's basically proven out.
So if people are interested in putting these into their systems, where should they go? What should they do? Who should they talk to?
Yeah, so they can really just go to our website. We have a lot of good documentation on there. We have links as well. They can reach out to our sales team, and then they can put you in touch with our field applications as well, which can help you with any sort of question you may have on sort of designing efforts.
Well, Nick, we are out of time, but thank you so much for coming on and sharing your wisdom and expertise with us. I really learned a lot and had a great time.
Well, thank you for having me. It was a pleasure to talk to you.
Thanks again to Nick Czarnecki from Allegro Microsystems, and thank you to Mouser Electronics for sponsoring this tech chat. To learn more about these multi-axis linear and angle sensors from Allegro Microsystems, head over to mouser.com/Allegro. I'm Daniel Bogdanoff, and I'll see you next time.